Alright, we're going to look at a really important topic. We're going to look at forces and we're going to look at Newton's laws of motion. Basically, everything that describes everything that happens in your everyday life. Quite important. We're going to do these things. But let's start off with what is a force. Well, what can a force do? We define a force by what it can do. And I can accelerate something, I can change its speed, or I can change its velocity. Obviously that's the same as accelerating it. I could spin it faster, or I could change its shape. So we're going to define a force as something which transfers energy from one thing to another. If I exert a force on you, I'm going to transfer energy to you. They will accelerate and they can deform. We don't ever get asked these definitions, but it's really important for us to keep them in our head. So let's think of this. We need to know the names of the forces, and we definitely don't want to get them confused with things that aren't forces. So here's some common mistakes and things we need to think of. Don't ever do that. The gravity is the field which causes the force. Air resistance, momentum is not a force. Forces change the momentum. Forces can transfer energy, but they think forces are measured in newtons, capital M. Things like this are measured in joules. Tension's one people forget. It's a force that's in strings, anything that's being pulled. Friction between two solid objects. Contact force, anything in contact. Okay? This guy's hand on his back, anything in contact. We call that a contact, you can call it a reaction force if you like. Upthrust or buoyancy, not flamboyancy, I was told once in the test. Upward thrust or buoyancy. Thrust, forward force from engines, quite a vague term, and lift, that's only for things that are flying, birds, planes, these kind of things. Learn those ones because we're going to have to label them, we're going to have to think about them. We need to draw force diagrams, and that's where these names come into it. Common mistakes. Not starting the arrows. Sometimes people draw them over here. Well, what's that on? I don't know. It doesn't make any sense. Let's draw them roughly from the centre of mass of the object. Making sure the arrows have this length, and their length depends on the size of the force. You've got big force, long arrow please, small force, smaller. Don't have to be too accurate, but I'm accelerating upwards, I'd like to see a big upward arrow and a smaller downwards arrow. If I'm in equilibrium, if I'm at constant speed, I want the arrows to be equal and opposite. Not labelling the forces. People forget to label them or get the ones wrong from the previous slide. Go back and look at it. You might do that. So let's look at these two. First one, we've got the rocket on the launch pad, over here, and then the rocket accelerating. Notice, arrows equal and opposite. I'm not accelerating. For upwards one, bigger, so I'm accelerating upwards. What are these? Contact force. I'm in contact with the ground. Weight or force of gravity. Definitely not just gravity. What's this one? Well, I'm going, still got the force of gravity downwards, and I'm going to call that thrust because I'm not touching the ground. It's not a contact force anymore. Alright, there's two good examples. What about this one? What's happening? Well, can you see, you can tell, without drawing anything, that I'm at a constant speed because my weight is equal to my air resistance. We can call that terminal velocity. All the information's in there. Alright, two laws. Very important. An object will continue to move in a straight line at a constant speed unless acted on by a resultant force. We'll come back to that in a minute. Now remember, you don't need a force to get you going forward. You don't need a resultant force to go forward. Because if you're going at a constant speed, that means there's no resultant force. Think about that. Second law. Why have I planned this out? Because people just put force here, don't they? No, that's resultant force. I need a resultant force because what does that cause me? It causes an acceleration. And F equals mn. Very important. What are my units? Newtons, kilograms, meters per second squared. Okay? First law talks about equilibrium. No acceleration, no resultant force. Second law, what happens when I accelerate when I've got a resultant force? Let's look at a couple of examples. I'm only going to pick out one here. Let's look at this one. I've got 7 and 5 going in the same direction. I've got 12 forward. I've got 4 and 6 going backwards, which overall gives me 2 going forward. Notice I've given an arrow, because what type of quantity is it? It's a vector, so I need a magnitude and a direction. Okay? We don't need to add forces in straight lines like this. If you're struggling, go and have a go at a couple. You could be asked to even think about the acceleration from this. Now, if you just have F equals ma and you put force equals mass times acceleration instead of resultant force, you might get confused here. Because you've got lots of forces here. But of course, we know that it's the resultant force. Can you see you've got 8 forwards, 8 backwards, no resultant force? That means no acceleration, it's a constant speed. Again, go and have a go at a couple of these. Alright, what's wrong with the following statements? Pause it if you want. If there's a resultant force, an object will move. Well, be more specific. A resultant force is called acceleration. An object is spinning. No, not really. It could be spinning at a constant rate. If I'm transferring energy, there must be a resultant force. Well, any force doesn't have to be resultant, can cause a transfer of energy. And if it's flying upwards from a bat, it has a forward force. No, it doesn't. Even if I'm going up, it's always accelerating downwards. Okay, you don't need a force in the direction of motion. That's a very common mistake. Alright, a couple of quick examples. A train moving at constant velocity has a resultant force in the same direction as the motion. True or false? Well, false. There's no acceleration, so no resultant force. What about this one? When dropped, a bowling ball will hit the floor at the same time as a golf ball. True or false? Let's have a look. Oh, it depends on the initial height. This is a really good one. If it's at low height, then drag doesn't really make a difference, and they're both going to hit the ground at the same time. If I drop anything on Earth, if we're ignoring drag, they're all going to accelerate at 9.81 or 10 meters per second squared at g. That's what g is. It's also often called the acceleration due to gravity. But if I've got a really big height, like I'm dropping them for a plane, then the heavier thing will have the higher terminal velocity, so the golf ball. That's one to trick your friends with. So think about this. Alright, we've got 1, we've got 2, and there's a third one. Now, this one doesn't really come up because it's quite hard to ask questions on, but we need to know what it is. Now, the best way of explaining it is that if body A, could be anything, acts on another body, let's call it B. So if I push this guy, then B, he, pushes me backwards with an equal and opposite force. I push the wall pushes back on me. The harder I push it, the bigger the force going backwards. Sometimes this is said every force has an equal and opposite reaction force, but that's quite vague. I mean, that'd be fine for GCSE, we need to know it, but this is a much better way of saying it. So, we looked at what can a force do, we looked at the types of force diagrams, Newton's 3 laws of motion, and some common misconceptions. Make sure you don't have them, go back and try it. Good luck.